Welcome. As part of a course on subRiemannian geometry, we will now revise some notions of differential geometry. In particular, I will recall the notions of vector fields and the Lie brackets between vector fields. And afterwards, we will recall the definition of Riemannian manifold and Finsler manifold. In differential geometry, the object of studies are smooth differentiable manifolds. So let's fix one, call it M, and say that the dimension, the topological dimension is N, is an N manifold. What does this mean? This means that, namely, our space is locally parametrized by open sets, open subsets of Rn, so that the change of coordinates are smooth functions, namely C-infinity functions. So the picture is that we have an object, and then for every point we can take neighborhoods and parameterize them with open sets from Rn, and then these maps, called charts, then when they intersect, then the change of coordinates from one chart to the other one is a smooth C-infinity functions from open sets of Rn. Okay, so now instead, if you have a map, so a map F from one manifold to another manifold, so map between manifolds, I will write MFT for manifold. The manifold is smooth if it is C-infinity after precomposing and postcomposing with parametrizations. Namely, right, so if you have a map between two manifolds, then what I have to do, I have to first go into the first manifold with a chart, then apply the map, then go with the inverse of that parameterization back to Rn, and if this composition is smooth, as for all choices of charts, I say that the map is smooth. Okay, let's talk about tangents. So for given a point on a manifold, the tangent space let's call it Txm. The tangent space at x of M is the collection of derivations of germs of smooth functions at x. What does it mean? Okay, so in fact, let me give a little bit more concrete description. So each such derivation is realized by some smooth curve, let's call it sigma, from an interval, let's call it meno epsilon epsilon, into the manifold, that at time 0 passes from the point x And the derivation does like this. For any function, smooth function, from m valued into r, let's call it f, then it gives a real number. What is this real number? This real number is the derivative of the function along the curve. So okay, this at time 0. So this is the how a curve induces a derivation. Okay? So the tangent bundle of m is Tm, which is just this joint union of all these tangent spaces, equipped with a topology, actually equipped with even a structure of manifold. So it's equipped with the structure of n square manifold, such that its smooth sections I'll explain now, called vector fields, in coordinates according to x, x1, x2, up to xn, are of the form. Now, how? Okay, see, so we have this space Tm, which is this joint union of the Txm, and of course we can send every vector at x at the point x. So we have this map that gives the structure of bundle to Tm. And what is a section of a bundle? This is an inverse. So for every point, I choose a tangent point at that point. For any point x, I choose a tangent vector at x. These are the vector fields. But here the structure and differential manifold is done in such a way that the sections that are smooth are of the form like this. So in coordinates, the derivative respect to the first coordinate is a derivation, right? So there is going to be a first function times this derivation times plus an x dxn. So these are how you write in coordinates smooth vector fields. So let me say again, which could be, first of all, let me say it could also be written, this is how you usually do in calculus, as just a vector a1x dot anx. Right? This is how you write in calculus a vector field, just an n pool of functions. But we might write them like this, but we will really think of them as derivation, but it should be seen as derivation. How? So if I have a function a of x times some dxj, so this is a derivation. How does this act on a function? F at x, this is multiplies by ax, and consider the jth derivative in coordinates now we have of f. Okay, so this is how we write smooth vector fields. Okay, and this gives us structure tangent. All right, so now given a vector field, let's call it x on a manifold called M, we say that a curve, it's called the curve sigma from minus epsilon into M, is a flow line of x starting at P, so P is a point of M, if sigma at 0 is equal to P. And then if I take the derivative of this curve times t, then I exactly have the vector field at the point sigma of t. Okay, so we will write here, the lower index will write the point where this vector field should be calculated. So now this becomes a vector at the point sigma. So this is an element of t sigma t m. Okay, so we require this to be true for all t in the domain of definition. Okay, now flow lines are unique. This is just by the theory of ODEs, and have a maximal domain of definition. Good. Now we denote by, so t goes to capital Phi, lower index x, upper index t, variable p, the flow line, so it's unique and has defined for some maximal domain, the flow line starting at P. Then the map, instead, for every P associate the flow line starting at P respect to x at time t, so it might not always be defined. Okay, for a given t, some point might not have a flow existing up to time t, but supposing it exists, with this map will be called, it's called the flow of x at time t. Okay, now we are going to discuss the definition of Lie brackets and vector fields, and I will give several definitions, and some of them will use the notion of flow. Okay. So Lie brackets will be very important in subRiemannian geometry. So Lie brackets, so the bracket of vector fields. So suppose we have x and y vector fields on the same manifold M, and we are going to see them as smoothly varying derivations. Then the Lie bracket of between x and y is the derivation denoted with the bracket between x and y, that is x, y minus yx. Now, this should be thought as compositions of operators. Now, what is not immediately clear is why this object should still be a derivation. Okay, there's something to check. Okay, but this defines a vector field. So, it's easy to just one proof first that this defines a derivation, and then there is a correspondence with the vector fields given by as tangents of curves. Okay, so some exercise one can also do immediately with the definition is to check that this. Okay, this is very easy. We have anti-commutativity. And very importantly, you have the Jacobi identity, which is, so you write, so this is, tells you what happens when you bracket three vector fields. So what you have to do to remember how to write it, you write the vectors in some order, okay? And then you follow the circle three times, starting from different elements, and you always put the bracket in the same order. Okay, so this plus, so now I start with y, it's y z x, and then I start with z x y. Then I have to put the bracket in the same way, so I'm bracketing first the last two, and then this sum is 0. This is an identity. It's very easy to check that this is true. Okay, this is one point of view of what is the bracket. Okay? Other viewpoints. So, other viewpoint. So the first one could be as Lie derivative. As Lie derivative. So the vector field associated to a commutator, the Lie bracket xp, can be like this. So consider the vector field evaluated at the point flow respect to x times t at the point p. Now this one, you pull it back with the differential of the map x at the minus, right? So this map is smooth, so it has a differential. You can pull back curves and therefore derivations. So now this becomes, for all t, that becomes vectors at the point p, and it makes sense to consider the derivative in this vector space. Vector space. Okay, this is one formula. Another formula is as commutator of flows. So the vector field xp at the xy at the point p is, you do like this. You start with p and you flow p first along x for time t, then along y at time t, then along x again times minus t, okay, and then you flow again respect to y at times minus t, okay. So these two are negative times, or like minus front, okay. So now this is a curve. What's true is that this curve has first derivative 0, instead the second derivative of this curve really defines a derivation, and this is evaluated at p at 0, the derivative at 0 is the bracket. Okay, another very practical way of calculate the vector field is in coordinates. Calculate the brackets. So in coordinates, so if you have a vector field, you say, okay, sum over some functions, these are just functions, times the standard vector fields in Rn, sum over j, y, j, dj. Okay, maybe this one I denoted before d over xi, but this is also denoted sometimes as d over dxj, because these are really the j partial derivative. So this is equal to the sum over I and j of So xi di yj. So see, I'm derivating this function here, taking the derivative, minus yi di xj dj. So this is a formula for calculating coordinates the Lie bracket of vector fields. Let's move now to Riemannian geometry. Let's recall what's a Riemannian manifold. So a Riemannian metric, or maybe better metric tensor, on a manifold M is a family of for now we'll just call them just functions of functions. So let's denote it by rho of x, where x is in M, such that, so first of all, for all x, the function rho of x as domain txm times txn. So the variables are pairs of vector fields at the same point x, and it gives a real number. But not just this function is a positively definite bilinear form. So in other words, it's a scalar product. So this is the first condition. Okay, so at every point we have a scalar product, and now we need to assume that the scalar products are changing continuously or smoothly. So the way we can impose this, requiring that for all smooth vector field, okay, just two of them, x and y, so these are vector fields on M, the function that for every point it assigns the real number given by the scalar product of the vector fields at that point. We're requiring that this function is smooth. So this is what is a Riemannian metric tensor. A Riemannian metric is also denoted by just with this standard symbol of scalar products. Okay, but with the idea that when you write, so if you have two vectors, let's say vector field x and y, and then this is vector fields at x, this is just the above function rho at x of the vector fields at x. Okay, in the terminology, we say that the pair M smooth differentiable manifold and a choice of a metric tensor, Riemannian metric tensor, this is a Riemannian manifold. Okay, how can we also define locally a Riemannian metric? Metric can be defined by an orthonormal frame. What does this mean? What does this mean? This means that we need to choose, so the choice of vector fields x1 up to xn Here I recall that n is the dimension of the manifold, that are at every point linearly independent. Linearly independent. In other words, like x1 evaluated at x, xn evaluated at x, these are linearly independent, therefore they are a basis of txn. They form a basis of txn. Now, in this case, there exists a unique Riemannian metric for which x1, xn are orthonormal. So let's evaluate it at x are an orthonormal basis of for txn. How do you calculate the scalar product? So if v and w are vectors txm, so we can write v as sum over a linear combination of the xj's evaluated at x. Likewise for w. And then the scalar product between v and w at the point x, this is the sum of aj, bj, sum over j. Okay. So this is what are smoothly varying scalar products. Now let's generalize this to the Finsler geometry. Okay, what's a Finsler structure? Okay, there are many variants for Finsler structures. So what they are always there. They are so there are variations on. So they are generalizations of Riemannian geometry. So structures. So and one can do different types of generalization, but the first idea is that one just replaces scalar products with norms. Okay, one should also pay attention what is a norm, what's a smooth norm, and which regularity we also require. And there's also some further generalization that one can ask if we really still want the norm to be symmetric. So in this course, in our discussions, we will always assume a symmetry. Right? This. And the reason is because we want to induce distances, and distances are symmetric. Okay, but the notion of Finsler structure is not a fixed one in the whole mathematical theory. So pay attention when you read some text about Finsler structures. Okay? So here's my definition. I will make it very, very, very general. Still, this is the barely thing that I need to make it then induce a distance. Okay, so I will call it a continuously varying norm on a manifold M is a function. So let's denote it like we did before with the standard symbol of scalar product. I will use the standard symbol of norm. It's a function defined on the whole tangent space, valued into 0 plus infinity. So it will not have possibility with 0 vectors of negative norm, such that, so first, so this is continuous. So it doesn't mean for all vector fields on M, the function that associates P to the norm of the vector at P, so this is a function from M to R, this function is continuous. And the second condition is that when you restrict to a given tangent space, this is a norm, a symmetric norm. Okay, what does this mean, a norm? Let me go on the next page. So what's a norm? A norm, i.e., so it should be homogeneous. So the norm of lambda x is equal lambda norm of lambda norm of x. So it should satisfy the triangle inequality, x plus y as norm less than the norm of x plus the norm of y. And 3 should be definite, positive definite. So the only vector that has norm 0 is the 0 vector. Okay, and this is so for all real lambdas and for all x and y in the same tangent space. Okay, so once we have a smoothly varying norm, in this course, we will say that the pair M and the norm is a Finsler structure or Finsler manifold. And it should be extremely clear that if you have a Riemannian structure, then this is in particular a Finsler structure. Okay. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.